Here's the code again. And that's my dog. And you know, guys, like, yeah, but she has a little hand. She looks like a flower. I was like, what that's true. Okay, are we ready? We're gonna stop talking, guys. We're good?
Yeah, we're good.
Okay, just checking. Okay, so the first thing on this chapter is gonna be all about IUPAC, because all of the reactions that you're gonna see here are gonna be with ketones and aldehydes, which is actually something that we talked about in chapter 12 when we were doing reductions, right? Now, we have to learn how to name them before we do any of the reactions. So what's gonna be the ending for aldehydes and ketones? He said it in class.
AL for aldehyde.
Mm-hmm. Beautiful. Okay, now remember previously your alcohol group had the highest priority. Now the carbonyls are going to have the highest priority. So let's say they were starting with that molecule. Where am I going to start counting? In which carbon?
The one with the double bonded
Mm-hmm.
carbon.
Exactly. So what do we think is going to be the name of the parent chain?
Pentane. No, it's 3-methyl pentan 1-pentanal.
Pentanol, yes. And that's it. Pretty simple. We're just counting the carbon chains. The one over here. What kind of functional group do we see? Ketone. So the ending is going to be one. What's going to be the IUPAC name? That's the common name. Propanone. Or we can also. You can be more specific, but in this case, it's not really necessary. It's kind of like obvious that it can only be in carbon 2. But you can put 2 propanone.
If it was carbon 1, let's say, then it would be propanone.
Mm-hmm. Okay, next one. We should know this one, actually. I think I put it in the chapter 15 handout. Not quite sure, though. What do we say? It's a phenol, yes. And what's going to be the common name for this one? This one you should know. Good job, Kayla. Yes. Acetophenone. That's going to be the common name that you should remember. And this one can be for chapter 15 as well. That is so way. This one should be simple. What's the name?
No, wait, no, it's not.
It is an aldehyde. What's it's actually going to be ethanol. We have 2 carbons, 1 and 2.
Oh, right.
So far, questions. So far, we're good. Pretty simple. We're just counting. Okay, for this one, what's going to be the full IUPAC name?
Two F. No, 4F. 2 pentanone. Oh, pentanone.
Pentanone. Does everyone agree?
Oh, it's X four. Four. Right.
It's actually gonna be 6, remember. The parent chain has to be the longest carbon chain. So it's gonna be 4-methyl, 2-hexanon. Very last one, IUPAC. Two what?
Oh, right, okay.
Propanol. And that's it. How do we feel about IUPAC? Pretty simple. We're just counting. We just learned a new ending. That's it.
Really quick, that benzene one is, but what's the like substituent and what's the parent chain?
What's the substituent? What's the parent chain? Technically, this is the parent chain
Okay.
because that's my ketone. And then this is going to be my phenyl group. For this one, we usually use a common name. Like your professor has never like really mentioned the full IUPAC name, so yeah. Okay, so far no questions. So let's start talking about the reactions. Okay. Now, and the next part is how to make your dear aldehydes. We already know how to make aldehydes. Do you remember them?
Oh, the oxidation cleavage.
It's oxidations, exactly. What can be one of the reagents that I can use?
O3.
O3?
Ozone.
That's ozonolysis, different reaction. PCC, exactly. As long as it's some sort of weak oxidizing agent, you're good. That's it. It's a really long name, so the only portion that I remember is DMSO, but it has a few other things. So yeah, it's not just DMSO. DMSO is just one of the common solvents that we have. Okay, so in this case, practically for you guys, for WES students, you only have to know this first reaction. Okay, what kind of functional group are we starting with? What's the name of this molecule?
Ester.
Beautiful. It's an ester. What's the name of the product? Functional group. Aldehyde. Are we oxidizing or reducing the molecule? We're reducing the molecule, exactly, because we don't have as many bonds between carbon and oxygen. Now, the only reagent that you should know for this portion to make your aldehydes is going to be your diol reaction. And that's it. If you're taking Dr. Roche, then you have to look at the other ones because he might test you on it. But for WES, it's just the one on the square. That's it. Diol. DIBAH. Okay, so far questions. This is basically just memorizing the reagent and that's it. And please start reviewing chapter 12 because it's going to come in handy for this chapter. Yes. No, he's not going to trick you with the temperature. No.
Because that's very cool back there. That's like.
Yes.
And the bottom two have West.
No, they're just for Dr. Roche.
Oh, yeah.
Okay. Which one? Which catalyst? Specifically, what does it do? How does it speed up the reaction? I lost you there, that's okay. Okay, So first of all of the reactions that you're gonna see in this chapter are gonna have some sort of catalyst. Different products can be created if you use an acid or a base catalyst in a few reactions. Now, they're gonna have different effects. They're both gonna speed up the reaction, yes, but specifically, your acid catalyst is gonna be just reacting with your electrophile, which is gonna make it more electrophilic. So in this case, it's just gonna makes the electrophile more electrophilic. That's it. That's the conceptual question that he's definitely going to test you on. Acids, they make the electrophile more electrophilic, yes.
So then the base catalyst makes the nucleophile more nucleophilic.
Exactly. The base is just going to make. They're both speeding up the reaction, but in different ways.
Base catalyst reaction.
Yes. Now in chapter 12, whenever we were doing any reductions, the carbonyl portion, what was that for the reductions? Electrophile or nucleophile? Electrophile. It was electrophile. So in this case, our carbonyl is still going to be acting like an electrophile.
Oh, right.
Because it's the one that's getting attacked. So for questions on the concepts, pretty simple. It's just memorizing them. Yes. Nucleophile is the one that attacks. The one that's being attacked, electrophile. Yeah, because we're either like breaking or making so many bonds. That's it.
So the nucleophile is giving off electrons.
Yes. Neutrons?
The nucleophile of electrons.
Yes, it's giving you neutrons, sorry. Electrons. Okay. Let's start with the reaction. So there's quite a few, and I'm gonna show you the mechanism for each of them, but there's also a shortcut. Okay, so just keep that in mind. If you freak out, it's okay. There's a shortcut. I'm not just gonna show you the shortcut. Okay, but before we actually go through with the reactions, remember, this chapter is only reacting with ketones or aldehydes. So in this case, I want you to notice basically the little legs of each of the structures, which are those portions in here. We have two R groups, and on the last two, we have R group with a hydrogen. Now, the ones in green, that means that we start with some sort of ketone. That's the only one that had two R groups connected to the carbonyl area. If we have an R group and a hydrogen, we start with an aldehyde. Okay, so always look at the little legs that your molecule has. Okay. Now, you guys are gonna have to know the common names for the products and the reagents for each of the reactions that you're gonna see here. Now, in this case, we can see that our little x tells us that we start with a ketone. So first portion is just gonna be a keto, okay? That just means that it comes from a ketone. But we can see that in the arms, we have, what kind of functional group is that left?
Ether.
It's an ether. And on the other side, we just see an alcohol group. So whenever they don't match up to each other, that's gonna be the hemiketo, okay? And now similar process is gonna happen over here to the right. We have keto refers that we start with a ketone. Because if we have the same molecule, same arms different, but the legs are from an aldehyde, then this guy is gonna be called your hemiacetal. The acetal is just telling you that you start with an aldehyde, sorry. Okay, so for our questions, we're all following, we get it? Okay, now, whenever we have practically the same product, but now our arms match up to each other, we have ether groups on both sides, that's gonna be the full form of the keto and the acetyl. So this one on the left comes from the ketone, it's just keto. And then we have our acetyl. So far, questions on that? Practically, if your arms match up to each other, it's just the full form. If they don't match up with each other, then it's the hemi form.
Heavy.
Yeah. I'm sorry? This one we should know actually. What's the common name for that one? Best guess. Diol. Be more specific. Are they vicinal to each other? Are they, what was the other term that we used? It's a geminal diol, it's a gem diol specifically. So this guy is just your gem diol. And that's it. Yes, thank you for telling me. Okay, now we know how to identify the products. We know their common names. Now we're gonna learn how do we get to those guys. Okay, and let me know when you guys are ready. Yes. It will still be a gem diol, yes. So in this case, let's just add actually just 4H. That represents that it can be both a ketone or an aldehyde. Okay. Seems like we're kind of good. Move on, hopefully. And in this case, we're gonna see what's gonna happen with both an acid and a base catalyst. So that concept that we talked about before makes more sense. Okay, so let's start with the acid catalyst one. Let's just start with a simple ketone. Specifically, that's just acetone. Now, this reaction is going to be the formation of a gem diol. Okay, so that's the one that has two alcohol groups coming from the same carbon. Now, the reagent for that one is very simple, actually. It's just water. So whenever you see water plus a ketone, you're always creating a gem diol. If you see an aldehyde plus water, you're still creating a gem diol. Okay, so remember, from now on, it's just basically memorizing initial molecule, reagent, final product. That's it. And now in the bottom, just let's say that we have HCl as an acid. Okay. Okay. How does the acid speed up the reaction? Exactly. And in this case, we know that the carbon over here is going to be the electrophilic portion, because we know that with the dipole moment, we get a delta positive and delta negative on that oxygen. We're going to see that. Okay. So remember, electrophiles, they're going to be better whenever we see charges. Specifically, electrophiles prefer a positive charge somewhere. Nucleophiles, they prefer a negative charge. Now, in this case, our oxygen is going to be attacking our acid. And this is just an acid-base reaction. So we can add that hydrogen in there, and now my oxygen is going to have what kind of charge? Positive. So now the carbonyl region is more electrophilic because now I have a full positive charge. So now I can proceed with a normal reaction. So at this point, let's just draw water in here. Okay. What was the very first step in our reduction reactions? Do we remember? For reductions, no, and no.
Will the oxygen, does it have right that level?
Nucleophilic attack, what's gonna be the nucleophile? From? Which oxygen? Yes. So whatever you see in the arrow, that's always gonna be your nucleophile for the reaction. So this guy is just gonna be doing the nucleophilic attack to that carbon. Remember, nucleophilic attack, that means we're making a new bond there. And then to not break the octet, we're just gonna push up the electrons to the oxygen.
So the HCl that protonates that oxygen initially, you said it's a catalyst, so it speeds it up, but let's say the HCl wasn't there.
The reaction is still gonna proceed, but not as fast. That's it.
So then that O will get protonated by the water. essentially.
Yes,
Okay, I see that.
we have our hydrogen there. And then we connected water. What do we think is gonna happen now? This is my final product.
So, then is the CL coming back in to grab the ice?
Exactly. My CO from the very first step is just coming back. And it's taking away one of those hydrogens.
Question,
Yes.
but when you protonate an oxygen, why does the oxygen not break off from that carbon? You know what I'm saying? Because I've seen reactions where you protonate the oxygen and then it becomes the leaving group.
Yes. And we're actually gonna see that actually for chapter 17. And that's only whenever you're looking at a carbonyl that has those, basically the leaving groups and the legs. The leaving group has to be in the legs of the carbonyl. So in this case, we had a ketone. The legs do not have any leaving groups. But if we had an ether, for example, on one side, then that's gonna be your leaving group. Similar to what we saw in your reduction of esters. That oxygen in the legs, that was your leaving group. That's the one that you can protonate and kick it away. What's the common name? We should know. It's just the gem diol. And that's it. That's how the reaction works. Very simple. That's it. Questions on the acid catalyst? We're good? Let's see how the base is going to affect the reaction now. And let's start with the same exact molecule. As soon as I see water, I know that I have to create my gem diol. And now at the bottom, let's just add sodium hydroxide. So I know that sodium is just an excitator ion that goes away. You're left with the very reactive base. And now, what do bases do? They make the nucleophile more nucleophilic. So what do we think is going to happen in that case? What am I going to attack? And what's going to happen? Make it HO, so we can have that negative charge. Remember, the electrophile is better with positive. Nucleophile better with negative. So in this case, it's just an acid-base reaction. We take away that hydrogen. And then we're left with this guy. OH minus.
Where does that post on?
It goes to the bottom. And then technically sodium is still there, but again, excitator ion, we don't really care about it. Okay, now we made the nucleophile more nucleophilic, so now we proceed with the normal reaction. So what's going to attack what?
So there's a partial positive on the bottom, so then it always comes on the bottom.
So yes, now my nucleophile that's better is going to attack my carbon. And then I kick up the electron, so I don't break the octet. So now I have an O minus that came from the carbonyl group, and then I connected an alcohol group from the nucleophile.
Why would you not just use sodium hydroxide directly to, yeah.
Just attach it there. I mean, you could do that too, yeah, but that's not gonna make the reaction happen any faster. Because it's practically like doing the reaction with no catalyst. It can proceed, yes, but the goal is to make the reactions happen faster.
We just have, so, because I see what we do is, you have H2O and OH, and all the OH does is pull a proton from the OH on the other one, so it becomes OH. Did you see what I'm saying?
Yeah, it's practically the same thing, but technically doing this way, even though it looks like more steps, it technically happens faster in a way. But the actual like full reasoning behind it, like I can't tell you.
Oh.
Like I cannot tell you. Exactly. And that's it. And we still created the same exact molecule. But notice how the mechanism is slightly different. For one reaction. For this one, no. Plus, once we're done with all of the mechanisms and all of the reactions, I'm going to show you the shortcuts. Water creates gem diol. Yes. Water, gem diol, always.
So then the other, like, the hemi, all that stuff, so it's gonna have an acid-base catalyst that do pretty much.
Yes, but they're going to create different things this time.
Right, I get that.
Okay. So for the first reaction, formation of gem diol, we always create the same exact product. It doesn't matter what kind of catalyst you do. But the only reaction in where it's actually going to affect the product is going to be your acetyl and ketyl formation. Okay. So remember, we can have either like the hemi form or the full form of a ketyl or an acetyl. So in this case, let's see what's going to happen with both acids and bases. Let's start with the acid one, and then we're doing the base one. And then let's just start with the same exact molecule. And let's use the same acid, HCl. Okay, now the reagent for this reaction is just going to be some sort of carbon chain that has an alcohol group. So I can just write ROH. Remember, the R just represents any carbon chain that you want.
In practice, there will be some type of ROH.
Yeah. It can be that. Again, any carbon chains with your alcohol group. Now, if we have an acid, how do we make the electrophile more electrophilic?
It has a positive charge on the OH. Yeah, probably the wait on the O. Remember you think about
Yes, by doing what?
it probably the O attacks the.
Yes, the oxygen in here is going to attack the hydrogen in your acid, which now makes that oxygen with a positive charge. Okay, so now we're good. We made the electrophile more electrophilic. Now we can proceed with the normal reaction. So that's when your alcohol group is going to come into play. And actually, every single first step in each of the reactions starts the same way. So what do we think is going to happen in here?
So the oxygen on the alcohol attacks the W1.
Exactly. Remember what's your nucleophile and what's your electrophile. So this oxygen here, and your nucleophile, it's attacking my delta positive in that carbon, and then I kick up the electrons so I don't break the octet. So I have that alcohol group that came from the carbonyl, and then I attached a hydrogen plus my R group, which means that I have a positive charge in that new oxygen. What do we think is going to happen now?
So the Cl is going to come back.
Exactly, we have to make everything stable. So this guy, whoops, takes away that hydrogen. And now you're left with a molecule that looks like this. What's that? What's the name of that? It's a hemiketal. Remember, first thing you're gonna do is look at the legs. We just have R group, so it has to be some sort of ketal. If we see that the arms don't match up with each other, hemiform, that's it. Now, what you should know is that your acid catalyst for this reaction specifically is gonna be a lot better than a base catalyst. So because it's a lot better, that means that the reaction can happen again. So acids are actually not gonna stop at the hemiform. They're gonna keep going. So basically you're just repeating the step one more time. This was your hemiketal, but you wanna repeat everything once again so we can get rid of that alcohol group. And then we can finally create this guy. Oops. Let's do this. What's the name of that molecule? It's just a keto, exactly. Okay, so for questions. Again, main point is that acid catalysts, they're gonna be a lot better for this reaction. And let's see what's gonna happen with our base catalyst now. We have the same exact reagent, but now we have sodium hydroxide. Okay, what's gonna happen in the very first step with a base catalyst?
It's gonna attack your other reagent, make more of the.
What's gonna attack my what reagent?
So the Na goes away, the O comes in and attacks, it gets rid of that H on that R group on top, yeah. So then you're left with RO.
Exactly. Oops, RO minus. No, what's gonna happen? It's gonna attack the carbon.
Yeah.
Exactly. Now we have our best nucleophile. So now we just attack our delta positive, exactly. And again, because it's a nucleophilic attack, I'm making that new connection to my OR group. Okay. Now, what's gonna happen? How do I neutralize this? With what?
Oh, okay. So water.
Exactly, because remember on the first step, this guy turns into water, an H2O. So water just comes again, and it's gonna be donating one of those hydrogens. What's the name of that molecule? Hemiketal, exactly. Now, the main difference is that bases are going to stop at that intermediate. They're always going to stop at the hemiform. The acids are the only ones able to complete the entire reaction until the very end. Questions so far? We're good? Okay, I'm going to stay there. But yeah, pretty much notice how there's a little pattern so far. What's the main gist of the reactions that we just went through? Do we see any common patterns in there?
Or the way that the
Well, that too, yeah. What else? What's the main change that you see? Describe the change of the product.
I guess it's the
What about the configuration? Sorry, the hybridization. How is that changing?
hydration state.
From initial molecule to final product.
If the oxidized.
sp2 to sp3. That's the main transformation. So keep that in mind. Yes, Nikki. So the actual reasoning behind it, I do not remember it. I just remember that your acids are going to be the only strong ones enough to proceed with the entire reaction without stopping at the intermediate. Bases, they make the reaction fast, but they don't have that push to do the full reaction. But the actual reasoning, you can ask your professor. Okay, we're good? Okay, it seems like we're good. Now, before we actually go through the mechanism of the new reactions, let's start looking at the products. Actually, before we do that, really quickly, what's the difference between amines and amides?
Amine is an NH2. Amide is double bond.
Mm-hmm. So please remember, the one that has a D, it has a carbonyl. If it has an N, pure single bonds. That's it. Okay. Yes.
Oh. That's amide.
This one's okay. So yeah, exactly. Just remember that. Please remember. Okay, now. Remember, when we're trying to identify what kind of molecule we're going to create, always start by looking at the legs. So we just have pure R groups in here. So that means that we're all starting with just ketones. Now, in this case, the name for ketones and aldehydes for the remaining of the reactions, they're going to be the exact same. So technically, you can just add a hydrogen in here if you want. It can be either a ketone or an aldehyde.
Also, the rest of the product is the same.
Exactly, yeah. Products are going to be named the exact same if you start with a ketone or an aldehyde. It's not like hemiketone. Yes, the common name. Like we had acetyl or hemiacetal. Those guys were different. Actually, no, sorry. Acetyl versus keto.
Yeah.
They're different. But in this case, you can start with either aldehyde or ketone. You're going to create the same structure. The structure is going to have the same name. That's it. Okay, now let's start with this little guy in here. So in this time, we have a double bonded nitrogen. And actually, maybe some of the ones who are taking lab right now know the name of this one. Who's taking lab right now? Okay. We're not that confident. That's okay. Amine. Beautiful. You got it, Valerie. It's an amine. Amine. That's it. It sounds really cute. Yeah.
Oh, press was downstairs. Yeah.
Oh my God. Either way. Okay, now. That's whenever your nitrogen is double bonded, specifically. Now, if your nitrogen is shifted and now it's just pure single bonds, what's going to be the name of that one? Maybe you guys know. No one? I'm not sure if you guys did this lab, so. I mean, okay, same. I'll give you that point. Yeah, technically you do have an amine in that section, but because we're adjacent, we're bisynyl to a double bond, this guy is going to be called your enamine, which sounds like enamine. So. Enemy. Okay, so now in this case, this one looks very similar to what other molecule? What was the name? Which one? Choose a molecule. Which is what name? Imine. Exactly, the imine. But the main difference is going to be that your imine has your double bonded nitrogen, but it's connected to some sort of R group, a carbon chain specifically. But if you see that your double bonded nitrogen is connected to another nitrogen, what do you think the name is going to be?
Imine.
Imine. Oh, no, it's actually, this one is not that funny, actually. It's your hydrosone.
Wait. Immunomod.
Oh my God, that was funny. Okay, now. This one, it looks similar to what molecules? You mean ants? No, we just did it. Hydrosone. It looks similar to the hydrosone and imine because they both have a nitrogen that's double bonded. But again, actually, you're trying to get there. Okay, so again, main difference, we have an alcohol group connected to the double bonded nitrogen. Imidazole. You guys are trying to say it like more what the actual name is. Any other guesses? Amazon. No. Hydro. We're not that confident. So this guy is actually an oxide. So yeah, there was no way that you guys could have guessed it, but still, it's funny. An M. Yeah, sorry. Remember, my handwriting is really crappy. Let's talk about the middle thing. So far, the only thing we've done is just name the products. Now, there's going to be a specific reagent that you should know, which is actually going to be this one. This guy, it's a reagent. The rest of them were products. No. That portion, which of the 4 molecules that we just named, it looks similar to? To which molecule? To the which one? You mean?
So what is the name of this?
Not the name. It looks similar to which molecule? Hydrosone. Exactly. Now, this is going to be the reagent for your hydrosone formation. So what do you think the name is going to be for the reagent? No. Diamine. Diamine. The name is very similar. Only one of the vowels changed. Hydrazine. You got it. The names are so. Yeah. No. If you get confused with hydrazine and hydrazone, hydrazine is going in, that's your reagent. Hydrazone, it's exiting.
Does it always have that double bonded carbon right there?
What double bonded carbon? This one?
The double bonded nitrogen carbon right there.
Yes.
That structure always did the same.
Yes.
Okay, so kind of looks
It kind of looks like a ketone. Thank you. Yes. So keep in mind, in the previous reaction, we were looking at the legs, right, of the products. That's the one that told you if you had a keto, an acetal, all of those guys. The legs of every one of the products, it's coming from the ketone and aldehyde. So keep that in mind. Whatever carbon chain you saw in there, it stays there.
So let's say like for the first one, like imine or something, you have the R group, and so this is a substituent, right? This imine, and then the name is based off of the other R groups. You know what I'm saying?
You lost me.
I just know doesn't have those R groups, right?
Yes, it
So
doesn't have.
that itself is hydrazone with or without the H at the bottom, right?
Yes.
But let's say imine with the R group, because those R groups can be anything.
Yes.
That's why they're there. So would it be whatever the name it is, imine?
Oh, are you talking about like figuring out the full IUPAC name of those guys?
Like,
No idea. No idea. These are just the names of the functional groups. These are new functional groups for you guys.
oh, right, okay.
Okay. So actually, we just have like 3 minutes or so. So we're gonna stop right here. So have a good day too. That was so fast.
Little bit.